we're getting dizzy with excitement. We're looking at quantum spin and quantum angular momentum in general, really. But in any case, so we were saying last time that if we're talking about spin 1/2, can't have that for orbital angular momentum, but spin 1/2, meaning that the total angular momentum on number is 1/2, then it turns out that if we want the z direction to be the one where the component is well defined, has a well defined value of the angular momentum, then we can represent the operators for the three directions. The x component of angular momentum, spin angular momentum operator, can be written as h bar over 2 and this 2 by 2 matrix, 0, 1, 1, 0, and we can take sy to be represented by h bar over 2 times the matrix 0, minus I, 0, and S sub z is h bar over 2, 1, 0, 0, minus 1. So those are the three component vectors there, three component operators. These guys satisfy the fundamental angular momentum commutation relation that Sx commuted with Sy, which means literally do the matrix multiplication Sx times Sy, subtract from that the matrix multiplication Sy times Sx. You can verify for yourself that that gives IH bar times S sub z and cyclic permutations. And so these guys do represent angular momentum operators because they obey the fundamental angular momentum operator commutation rules. The vector operator representing the angular momentum would then be written as kind of this funny beast, S sub x times x hat. The operator S sub x times x hat, so it's a matrix times the unit vector x hat plus S sub y hat plus S sub z hat. And if I wanted the operator for the component of angular momentum along some direction specified by a unit vector n hat, just some n hat that specifies some direction in space. And n hat is just r the vector over r its magnitude. So in other words, n hat has components given by let's see what we picked sine theta cos phi x hat plus sine theta sine phi y hat plus cos theta z hat. Because r as a vector is r times that. So r sine theta cos phi is the x component. R is equal to x. I mean r sine theta sine phi is equal to y. R cos theta is equal to z. So if you divide by r, we get a unit vector pointing in some direction, specified by the polar angles theta and phi. And if you think about it, that's what you need in 3 dimensions to specify a direction uniquely, because theta and phi are latitude and longitude, if you will, actually co-latitude and longitude on the surface of the sphere. And so from the center of the sphere, any direction you like points to some latitude and longitude on the surface of the sphere. So if I knew the latitude and longitude of some point on the Earth, that uniquely specifies a direction from the center of the Earth to that location. We're doing the same sort of thing here, except we're using co-latitude and longitude instead of latitude and longitude. And to construct the operator which represents component of angular momentum along some given direction specified by n hat, you just take n hat dot the vector s. So you take it very literally. In other words, you would take sine theta cos phi times s of x plus, I should say, sine theta sine phi times s of y plus cosine theta times s of z is that operator. So in other words, you would construct the matrix, which was sine theta cos phi times the sx matrix plus sine theta sine phi times the sy matrix plus cos theta times the sz matrix. That matrix, that 2 by 2 matrix, is the operator which which represents the component of the spin in direction n hat. And one of the problems, you get to do that basically. Okay, any questions? And suppose we want the operator which represents the total angular momentum, the total spin angular momentum squared. How would we construct that operator? What would that be equal to? Yeah, it would be sx squared plus sy squared plus sz squared, because the square of a vector is the sum of the squares of its components. But here, when we're looking at an operator, we are looking at, by sx squared, we really mean take the matrix sx and multiply it by itself. And similarly for sy squared, and similarly for sz squared. And I'll let you do it, but what you get when you do all of that is that it's equal to 3/4 times h bar squared times the identity matrix. And then remember we said that if I want the state which represents spin up, if you will. So in other words, has total angular momentum quantum number s equals 1/2, and for a spin 1/2 particle, that's the only possibility. It's intrinsic angular momentum, so its total spin quantum number is 1/2. And if we want the m sub s value, the quantum number associated with the z component of the angular momentum, then we said that we would represent that with a beast called chi plus. And if we don't put the superscript, it's understood to be a z. In other words, just chi plus by itself means the eigenstate for the z component of the angular momentum, and that was equal to column 1, 0. And 1/2 minus 1/2, which we represent as a column vector, which we call chi minus for the z direction, is 0, 1. And those are the two eigenvectors of the sz operator, because if I take sz operator and apply it to chi plus, and here I'll go ahead and use the superscript z to indicate that it represents an eigenfunction for the z direction, then that'll be h bar over 2, 1, 0, 0, minus 1 times 1, 0. And if I multiply 1, 0, 0, minus 1 times 1, 0, what do I get? top component 1, right, because I get 1 plus 1, 1 times 1 plus 0 times 0, and then the bottom component is 0 times 1 minus 1 times 0, which adds up to 0. Yeah. Meanwhile, it's multiplied out front by h bar over 2. And so this is, in fact, h bar over 2 times chi plus for the z direction. So that gives us what we want. In other words, that chi plus is an eigenvector of s sub z with eigenvalue h bar over 2. S sub z times chi plus gives number times chi plus, the number is h bar over 2. And with the usual quantum rule that the eigenvalue, if you have a thingy which is an eigenvector of an operator, then the eigenvalue is what you're going to get if you make a measurement. So chi plus represents the wave function, if you will, for a state which has well-defined z component of angular momentum equal to h bar over 2. And if we apply sz to chi minus, we get h bar over 2, 1, 0, 0, minus 1, hitting 0, 1. When I multiply those matrices together, what's the top component? 0, right? Because I get 1 times 0 plus 0 times 1 is 0. How about the bottom component? Minus 1, because I get 0 times 0 plus 1 times minus 1 is minus 1. There's an h bar over 2 out front, so I get h bar over 2 times the vector 0 minus 1. But that's the same thing as minus h bar over 2 times the column whose components are 0 and 1, but the column whose components are 0 and 1 is chi minus. So this is minus h bar over 2 times chi minus for the z direction. So chi minus is also an eigenvector of the s sub z operator with eigenvalue this time minus h bar over 2. So chi minus represents a state that has well-defined z component of spin minus h bar over 2. Any questions? Meanwhile, are those guys eigenvectors of s squared? Well, s squared is 3/4 h bar squared times the identity. Is there any vector which is not an eigenvector of the identity? No, because identity times any vector gives the vector back. So certainly then s squared applied to chi plus gives me 3/4 h bar squared times chi plus. And s squared applied to chi minus gives me 3/4 h bar squared chi minus. But in fact, s squared applied to any combination of chi plus and chi minus gives you 3/4 h bar squared times that same combination back again, because the identity has every vector as an eigenvector with eigenvalue 1, or multiplied by 3/4 h bar squared, so the eigenvalue is 3/4 h bar squared. Does that make sense? Well, s sub z should have eigenvalues m sub s times h bar, and by labeling these guys with 1/2 and minus 1/2, we were just saying that, in other words, the eigenvalues of s sub z are plus and minus 1/2 h bar, plus if you're looking at chi plus, minus if you're looking at chi minus. Plus 1/2 or minus 1/2, so s sub z can be, if it's well defined, 1/2 h bar or minus 1/2 h bar. Even if it isn't well defined, if you make a measurement, you can only get the possible eigenvalues, so you can only get 1/2 h bar or minus 1/2 h bar. Meanwhile, s squared should have values of, well, it's an angular momentum, so how's it work? S squared should be what times h bar squared? For orbitoangular momentum, L squared was what times h bar squared? It was L plus 1. Total angular momentum quantum number times itself plus 1, h bar squared. Same deal here. S squared has to be little s plus 1, h bar squared. What's little s here? 1/2. So it has to be 1/2 times 1/2 plus 1, h bar squared. What's a half times a half plus 1? 3/4. Yeah, 3/4 h bar squared. So this makes perfectly good sense, that if I measure the total angular momentum squared, I have to get 3/4 h bar squared, because that's the value of s plus 1 h bar squared when the spin is equal to 1/2. So that has to work out. So everything here has been consistent with how angular momentum ought to behave. In other words, we've got these operators that obey the angular momentum commutation relations, and we have these states which have well-defined values of s squared and s sub z, and have the eigenvalues you would expect. And furthermore, we haven't said it yet, but here's something else one can confirm. In fact, s squared and sz commute with one another. The s squared operator and the sz operator commute. That's trivial once we've got this representation of s squared, because the identity commutes with any other matrix, right? Because identity times a matrix minus matrix times the identity is matrix minus the matrix equals 0. So s squared certainly commutes with s sub z, and that means you can find states which are simultaneously eigenvectors of both operators. And in fact, we have found those states. 1, 0 and 0, 1 are simultaneously eigenvectors of the s squared operator and the sz operator, with the eigenvalues that we would expect, plus or minus half h bar for s sub z, and 3/4 h bar squared for s squared. Any questions? Do convince yourself that this is true. Go ahead and, on your own time, add xx squared plus sy squared plus sc squared, and convince yourself that it's equal to 3/4 h bar squared times the identity matrix. And then I think I mentioned last time that we can express S in terms of the Pauli spin matrices, as in Pauli exclusion principle. Wolfgang is also known for the Pauli, I guess it's really more Pauli spin matrices. As an operator, the vector operator S is h bar over 2 times the vector operator sigma, and sigma sub x is the pieces of the sx, sy, and sz operators that don't have the h bar over 2. In other words, 0, 1, 1, 0 for sigma sub x. S sub x is h bar over 2 times that. And sigma sub y is 0 minus I 0. And sigma sub z is 1, 0, 0, minus 1. The commutation relations obeyed by the sigma are sigma x, sigma y commute to 2I sigma z, and cyclic permutations. So before we've talked about a wave function, psi as a function of x, y, and z for an electron, and now we're talking about having, if you will, a spin wave function, these chi plus, chi minus that you can have. In general, the spin of the electron will be some linear combination of chi plus and chi minus. It'll be some upper component and some lower component, both of which are non-zero. And in general, then, the total wave function of the electron is a two-component vector, and each component is a function of x, y, and z. To combine spin and orbital degrees of freedom, we use a wave function of the form psi of x, y, and z for our electron is a two-component column vector. The top component we'll call psi plus of x, y, and z. And the bottom component we'll call psi minus of x, y, and z. We'll notice that that can be written as psi plus of x, y, and z multiplied by 1, 0 plus psi minus multiplied by 0, 1. Or in other words, it's psi plus chi plus plus psi minus chi minus. Psi plus chi plus plus psi minus chi minus. And here I'm reverting to not putting the superscript on the chi's. It's understood that we need in the z direction if I don't put a superscript. But the z direction is whatever direction we decide to make the shining axis by which all others are compared, so to speak. In other words, it's up to us what direction we want to quantize along as far as the angular momentum is concerned. So normally we just call that the z-axis, but we certainly do not have to. So what do you think psi plus squared represents? Physically, what would that represent? Probability of finding these particle, of finding the electron, spin up near x, y, z. Actually, we'll go ahead and put psi, so we'll put a dv there, which could be a little dx, dy, dz, or whatever appropriate volume element you want to use, is probability of finding, we'll make an electron, it could be some other spin one half particle, but an electron, an E minus, spin up in our little volume element dV. And psi minus, of course, squared dV will be the probability of finding the electron spin down in that volume. So notice that those relative probabilities could vary from location to location, certainly. So we've graduated to where now we can throw spin into the picture. Our electron can not only have a wave function that describes where it is, but if we give it two components, the upper component represents represents the chance that you'll find it spin up, and the lower component represents the chance that you'll find it spin down. In general, the electron doesn't have to be either spin up or spin down. In general, it's some linear combination of spin up and spin down at each point, because that's just the way quantum mechanics works. That in general, the particle doesn't have a definite z component of the spin angular momentum. It's a linear combination, a superposition of states with definite components in that direction. And then if we want to normalize, what we want to construct is, instead of psi star psi, we make psi dagger psi. Psi dagger psi dV, which is absolute square of psi plus absolute square of psi minus dV. That's what has to add up to equal 1. What is psi dagger? Psi dagger is the adjoint, so instead of a column, psi plus, psi minus, what is psi dagger? It's a row. Psi dagger is a row, and what are the two components of that row? The stars, right. Remember, when you take a dagger, you change a column to a row, and you replace with complex conjugates. So the components of psi dagger are psi plus star of x, y, and z, and psi minus star of x, y, and z. So if I take psi dagger times psi, I'm going to get psi plus star psi plus psi minus star psi minus, or in other words, psi plus squared plus psi minus squared, absolute squared, added together in order, and that's what you sum up together, the total probability being 1. So the probability of finding the electron at any given point is psi dagger psi dV. Any questions? All right. So there's nothing sacred about the z direction. We must be able to have states which have well-defined values of the angular momentum in, say, the x direction, or the y direction, or in general some direction specified by n hat. So let's ask ourselves, what are the eigenvalues and eigenspinors? Remember, we said these two component guys are spinners, so we'll say eigenspinors of, let's say, s sub x. What are the eigenvalues and eigenspinors of s sub x? Well, to find the eigenvalues, we could go to the trouble of doing the usual business of subtract off lambda along the diagonal, take the determinant, and set that equal to 0 so it doesn't have an inverse, and get a quadratic equation and solve for the lambdas that results in all that. But what does the physics say? We know if we measure the z component of the angular momentum, the only possibilities are plus h bar over 2 and minus h bar over 2. What about if you measure the x component of the angular momentum? What are going to be the only possible values you could get? Same ones, right? Minus h bar over 2 and plus h bar over 2, because there's nothing special about the z direction. I can call any direction the z direction, so it has to be true that no matter what direction I measure along, the only possibilities are the same ones that I get for the z component. So it has to be that the eigenvalues are plus and minus h bar over 2. So again, you can formally prove this by going through the problem of actually setting the determinant of S sub x minus lambda I equal to 0 and doing all that crap, but it has to be that you're going to get the same result as for z. So the eigenvalues must be plus or minus h bar over 2, since all axes are physically equivalent. So, since we already know the eigenvalues, we can jump right ahead to finding the eigenspinors. For plus h bar over 2, we'll have that S sub x times chi plus for the x direction. So the eigenspinor that has plus h bar over 2 along the x-axis, that's what chi plus with the superscript x represents, has to be equal to h bar over 2 times that spinor, chi plus in the x direction. So h bar over 2 times 0, 1, 1, 0 times, and we'll call it, say, A, B. Let the components be A and B of the eigenspinor. So S of x is the operator h bar over 2, 0, 1, 1, 0. That multiplied by whatever the components are, A, B of chi plus x, has to equal what? What do I put on the right-hand side? H bar over 2 AB. Operator times spinor equals eigenvalue times spinor, is what that's saying. So chi plus x, I'm just letting that be AB, and then this second line is just putting into specific form what the first line is saying. Sx operator times chi plus equals h bar over 2 times chi plus. So another way to write that would be h bar over 2 times minus 1, 1, 1, minus 1, A, B equals 0, 0. In other words, I just subtract off from both sides. If I, in other words, the other thing we can do is we can subtract the eigenvalues along the diagonal and then say that times the vector is equal to 0. If you don't like that, this is the way I've got it in my notes, but I'm seeing some looks of confusion, so I'll just.
When I read your notes, I stopped reading.
Oh, where I got that from was the fact that, remember that we can say that, how do I want to say it? That if the other way to do it is to, how do I want to say this? I could also look at this as being, if you like, you don't have to write this if you don't want to. That's true, right? In other words, if I just multiply by the identity matrix, I haven't changed anything. So I can say it's h bar over 2, 1, 0, 0, 1, AB, right? Now subtract on both sides. If I subtract the right side from the left side, that turns it into h bar over 2. And then subtracting, I'll get minus 1 along the diagonal. A, B equals 0, 0. Does that make you happy? now I subtract this matrix from, I subtract this from this.
Oh.
So I subtract this whole thing from this whole thing. If I do that, I get h bar over 2 times 0, 1, 1, 0 minus 1, 0, 0, 1 times a b equals 0, 0. Because if I subtract, I'm going to get the 0 vector on the right-hand side. So if I subtract the matrices from one another because everything else is the same. Which is really another way to look at it, is remember that we could go, if I didn't know what the eigenvector of the eigenvalues were, I'd say 0 minus lambda, 0 minus lambda, AB equals 0, 0. When you were finding the eigenvalues to begin with, you would make this equation, and then you would take the determinant and set it equal to 0. And then once we know what the eigenvalues are, then we just go ahead and solve this equation, plugging in the eigenvalue being h bar over 2. And so that would give us the minus h bar over 2's along the diagonal. So either way. But if you like, we can just do what we were writing to begin with here. Certainly I can start with this equation. So what does this say? What equations does that give me? Well, over here on the left, what is the matrix times AB equal to? What is 0, 1, 1, 0 times AB equal to? What's the top component? Yeah, I get B on top because I get 0 times A plus 1 times B. So I get B on top, and then on the bottom, what do I get? A, because I get 1 times A plus 0 times B. So I get B on top, A on the bottom, times h bar over 2, but there's h bar over 2 on both sides, so that's going to cancel anyway. So on the left, so I get that this is true, that the column B on top, A on the bottom has to equal to column A on top, B on the bottom. If I like, there's h bar over 2, but I'm going to cancel that. Right? So if I multiply through, there'll be h bar over 2, but I could cancel that common factor of h bar over 2 before I could do anything. So both of these say the same thing, namely what? What does this imply? What does this imply about A and B? That they're equal to one another. Yeah, both of those relations say that A is equal to B.
So whichever value we pick for A, we must give it to B
Exactly.
as well.
Exactly. So whatever A is equal to, B is equal to as well. So in other words, it has the form AA, or BB, or QQ, or whatever. Anything of the form AA, the two components are equal to, does the trick. But what do I want to do also as well? I want to normalize. I want to normalize. Yeah, I need to normalize this. Set A by normalization. And to normalize says to do this. It says take the dagger times the column and set the result equal to 1. So that would say A star as a row mention this, but each component with a spinner, the absolute square of that represents the probability that you will get that particular result from a measurement, the eigenvalue associated with that component with a measurement. So this multiplication, the spinner dagger times the spinner is equal to 1, and what does this result in? If I multiply this row times this column, what do I get? 2a absolute square. Yeah, so this says 2 absolute square of a is equal to 1. So we can make a equal to 1 over the square root of 2. Does it have to be 1 over the square root of 2? Yeah, a minus would work, but I can be even more general than that. If a absolute square is equal to 1/2, 1 over root 2 does the trick, but so does minus 1 over root 2. What about 1 over root 2 e to the I phi for some absolutely arbitrary phi? Would that do the trick? It sure would. There's always here, there's always a complex phase that you could multiply by, because when you take the star, it would turn into e to the minus I phi and it'll cancel out. So that ambiguity is always there. There's always an arbitrary complex phase in the normalization. And normally we just throw it away. We just say, well, let's make it real, just because we like to. But we don't have to. But we can take a is equal to 1 over root 2. So the conclusion is that chi plus for the x direction is 1 over root 2, 1, 1. Because both components are equal and equal to 1 over, and each one is 1 over root 2. So 1 over root 2, 1, 1 is chi plus for the x direction. It's worth doing a check. So let's verify that Sx applied to our chi plus gives us what we want. Sx is h bar over 2, 0, 1, 1, 0. And we're going to multiply that by 1 over root 2, 1, 1. So that's going to give me h bar over 2 times 1 over root 2 times what I get when I multiply 0, 1, 1, 0 by 1, 1. What do I get when I multiply 0, 1, 1, 0 by 1, 1? What's the top component? 1, right? 0 times 1 plus 1 times 1. What's the bottom component? 1. Again, 1 times 1 plus 0 times 1. And what's 1 over root 2, 1, 1? Chi x plus, yep. So in fact, it worked out that if I take chi plus x and hit it with Sx, I get h bar over 2 times chi plus x. So we have that happiness and joy that we did succeed in finding the eigenvector with eigenvalue h bar over 2.
Why isn't it the same as the z direction now?
I'm sorry?
Why isn't this the same as the z direction?
Because this, so if I take Sx and apply it to chi plus z, what do I get? I get h bar over 2 times, what do I get when I multiply 0, 1, 1, 0 by 1, 0? I get 0, 1. What's 0, 1? Chi minus, so I get h bar over 2 chi minus in the z direction. So is chi plus in the z direction an eigenvector of the Sx operator? No, it isn't. And that means that A state which has well-defined z component of spin does not have well-defined x component of spin. This is not surprising because Sx and Sz do not commute with one another. Therefore, in general, we do not expect them to have simultaneous eigenspinors. So in other words, what this is reflecting is that when it comes to angular momentum, you are allowed to know the total angular momentum squared and one component, but only one component. If you know one component of the angular momentum, you don't know any other component of the angular momentum. So in other words, if the wave function, if the spinor is chi plus, I know the z component of the angular momentum, but I don't know the y or the z or the x components. Here, I found the eigenspinor where I know the x component of the angular momentum and that it's equal to h bar over 2. This thing is not an eigenspinor of the sz operator. If I hit this with sz, I don't get sz back when I'm done times an eigenvalue. So that's why they're different, because they represent different physical states. Chi plus z has well-defined z component of spin. Chi plus x has well-defined x component of spin. You can't have both, so they have to be different from one another.
So, but for this thing, so if you have SZ applied to XZ plus,
Or chi z,
I mean, yeah,
yeah.
and so the direction, I mean, the axis we choose matter here, then?
Right. So it's different from saying, see, when I said that the eigenvalues have to be the same, that's because whatever direction I choose for performing a measurement, the possible results I get have to be the same. That's not the same thing as saying that a given state has to have well-defined angular momentum in every possible direction. In quantum mechanics, you can only know one component of the angular momentum. So that argument that I made applies to the eigenvalues. It doesn't say the eigenvectors have to be the same. They can't be the same because different states have different directions in which their angular momentum is well defined. But the eigenvalues have to be the same. The possible results of a measurement have to be the same. If that weren't true, we'd be able to define the z-axis as the one where we always get plus or minus h bar over 2. There would be a way to objectively determine what is the z direction by performing measurements and saying the z direction is the one where if I measure the spin of an electron, I have to get plus or minus h bar over 2. But that doesn't happen. Whatever direction I measure the spin of an electron in, I can only get plus or minus h bar over 2. But that's not the same thing as saying if I have an electron where it has well-defined spin h bar over 2 along the z direction, then I'll get the same thing if I measure in other directions. Another way to say it is, notice that we can say this, that chi plus x is equal to 1 over root 2 chi plus z plus 1 over root 2 chi minus z, right? Because chi plus is 1, 0, chi minus is 0, 1. So 1 over root 2, 1, 1 is 1 over root 2 chi plus 1 over root 2 chi minus. So in other words, chi plus in the x direction is a superposition of chi plus in the z direction and chi minus in the z direction. So suppose I have a particle, an electron, and I measure its x component of spin, and I get plus h bar over 2 as a result. And then I measure the z component of its spin. What possible values can I get, and what are their probabilities?
We can get a superposition of the h bar over square root, too.
Well, careful. If I measure it, I don't get a superposition. If I measure it, I always get a definite result.
Oh, well.
So the state before the measurement is superposition, but after the measurement, remember the wave function collapses into an eigenfunction of the operator corresponding to the measurement that we made. So if I measure the z component, the x component of the spin, and I get plus h bar over 2, then I know right after that measurement, the wave function, the spin wave function has collapsed to be chi plus x. Then I measure the z component of the spin. If I measure the z component of the spin, what possible results can I get? I can only get the eigenvalues associated with S sub z. What are the eigenvalues of S sub z? What are they? Yeah, go.
Plus or minus h bar over 2.
Yeah, plus or minus h bar over 2. Absolutely. I can get either plus h bar over 2 or minus h bar over 2, because those are the eigenvalues of S sub z. Those are the only things I can get. What's the probability that I will get plus h bar over 2? 1/2. Because remember that the absolute squares of the coefficients of the expansion are the probabilities. So the probability of getting plus h bar over 2 is the absolute square of the coefficient of chi plus z in that expansion. So I've got 1 over root 2 squared equals 1/2 as the probability of getting plus h bar over 2, and also 1/2 as the probability of getting minus h bar over 2. It's 50-50. On the other hand, what if I somehow knew before the measurement that the spinner was this linear combination? What if before the measurement I somehow knew that the spinner was 1 over root 3, actually maybe it's better to write it as square root of 1/3 chi plus z minus square root of 2/3 chi minus z. If I measure the z component of the spin, what possible values can I get? No, what are the, you're in the right direction, but the values I can get are the eigenvalues, right? So plus or minus h bar over 2, right? That's like knee-jerk. If I say, what values can I get for the spin of the electron, and if I measured in the direction, doesn't matter what is, the answers are plus h bar over 2 or minus h bar over 2. What's the probability that you'll get plus h bar over 2? 1/3. What's the probability that you'll get minus h bar over 2? 2/3, because it's the absolute squares of the coefficients that give the probabilities. So the probability of getting plus is 1/3, the probability of getting minus is 2/3. After I make the measurement, if I get plus h bar over 2 in the z direction, what will the wave function be? What will the spinner become? It'll just be chi plus, pure chi plus, because the wave function will have collapsed to be the eigenspinner of the SZ operator corresponding to the eigenvalue that I got in the measurement. If I got minus h bar over 2, right after the measurement, what will the spinner be? Chi minus. It will be pure chi minus. It's that whole business of you make a measurement, you collapse the wave function. Before the measurement, the coefficients tell you the probabilities. After the measurement, every other piece goes away except for the one that corresponds to the result that you got from your measurement. So this is all the usual quantum mechanics applies here, and so it's important to realize that while the eigenvalues are the same in every direction, that doesn't mean that a given state has the same value of angular momentum in every direction. I mean, that would be sort of crazy classically too. If I knew that the component of the angular momentum in the z direction was some value, that doesn't imply anything in particular about the x and the y components. And so it's not surprising from that standpoint. What's different from the classical case is that classically you could resolve the total angular momentum vector into x, y, and z components that were all well defined. But in quantum mechanics, no, we can't have anything like that. You know one component, but you don't know the other components. And the way we represent that is with one of these vector diagrams where we say, it's just a picture, but we say, okay, we imagine that the total angular momentum spin vector is precessing. If we got a definite value of plus h bar over 2 along the z-axis, we imagine that all we know about the total angular momentum vector is that it lies on this cone, because no matter where it is on this cone, its projection along the z direction is h bar over 2. But we don't know its projection onto the xy plane, because all we know is that it's on that cone somewhere, so we don't know its x and y components. And sometimes we picture it kind of randomly spinning around on that cone. Where it stops, nobody knows. But even that's wrong, because that picture has you thinking at any given moment it's somewhere, we just don't know where it is, when really the quantum picture is no, it's not anywhere in particular on there. It's just got, you know, different, all you can talk about is what the probability is you find it anywhere on that cone, and it's equal probability anywhere on that cone. But still, it's got a well-defined z component. Okay, so obviously our break will extend until 20 minutes after the hour instead of 10 minutes after the hour. So we'll take a break now, and then I will come back after the break and hand things over to Amit, because I'm not going to make you do the evals during break. That's not fair. You're supposed to be breaking during the break. So then we'll do the course evaluations, and then you'll come and get me, and then we'll have the glorious finish of today's class. And then we'll just be waiting for Thursday. Yeah, sure. Yeah, but just keep yeah. Yeah, that's right, yes. Yeah, right. I don't think that's probably not what they're thinking there.
Like, I know what they want.
Yeah. I don't know what,
Like,
yeah,
after you send them.
right. I'm not sure exactly what to tell you. I think I would say something like, you know, I haven't done any internships or summer research or whatever, but I did do this, you know, I think that's about